All right, guys. So we're gonna do a quick little introduction into labs and then specifically why we're graphing them. We'll start with the main question, like why are we graphing? Why do we have to graph? But it's the short answer. It's a quick way to compare two unknowns. We don't necessarily know if they're related. So we pick two variables and we graph it. We take measurements on one as we adjust the other one and we graph it. And then so it's used throughout physics. We'll do it every chapter. There's some relationship and I'll the chapter will pick the variables, but we're going to figure out what the relationship between those variables are. We're going to verify it. We know what the relationship is, and you're going to verify it. So so here's my example here. Which car gets the most miles per gallon? So there we took a car, right? And we made measurements. We drove a mile and we measured how much gas it used. Drove another mile, measured how much gas it used. And then we plotted it. Uh, and from that plot, and we're going to use computers to plot this stuff. We're not going to do it by hand. We can use a spreadsheet. I will talk about this when we get to the labs. Um, but we're going to plot that data. And then what you get is this thing called a best fit line. And just from looking at these, without even numbers, which car gets the most miles per gallon? Well, it would be the one with the bigger slope, which would be the steeper graph. So in this case, it would be the steeper one, this red one here. What are the slopes of the two lines? It's just right. This is just a reminder. It's rise over run. We are going to be using spreadsheet programs, so you won't have to actually pick two data points, take the change in the y divided by the change in the x. There's no reason to do that when you've graphed it digitally. You might as well let it analyze it digitally. And again, I'll walk you through that when we get to the labs here. This one real quick, just as a reminder on how it works, though. You should know how it works. It's just the computer's going to do it for you. But I'm just picking 104 because it's a nice little point, and then 0, 0. Those are my 2 points. So the change in the run, right? It goes from 0 to 100. That's a change of 100. I'm sorry, that's the rise. The change in the rise is 0 to 100. The change in the run is 0 to 4. So if I do 100 divided by 4, I get 25. And then here's the units also follow that rule, rise over run, miles per gallon. So that's what the slope means here. The slope specifically means miles per gallon. And in this case, it's 25 miles per gallon. You can do the same thing with this blue line, this less steeper line. I'm going to pick 50 because it's a nice point, 50 and 0. So the rise is 50, right? A change of 50. And the run is a change of 5, 50 divided by 5. It's a change of 10 miles. It's a slope of 10 miles per gallon. And then again, the computer's going to do that for us. I just need you to, in the back of your head, you should know what it's doing. It's just doing it a lot more and accurately and quicker. I mean, that's the main goal. We want to get it done quick. All right, measurements. This is only a worry in labs. We will talk about significant digits. Like I'll give answers in significant digits, but it's just something you should have in the back of your head, not something you're stressing about. All right, so why do we need significant digits? So it turns out, I don't know if you've thought about this or you've heard this before, but all measurements are an estimate. Regardless of the measuring device, you always have to end up guessing that last place because it's always going to fall between two lines. So in this case, I got a ruler here, a meter stick, 100 centimeters. There's one marking, right? It's just that whole bar. So I don't know, right? I know it's not fit, right? If I cut that in half, I know half is 50. 40's probably too far. 10's way back here, so it's probably not 10. It's 20, 30. I don't know. It doesn't have any markings, so I can't say 21, 22. I can't say 33. Like it's around 20 or 30. So that's my answer. If I gave you that meter stick, you might say 20, and the person beside you might say 30. So that meter stick is only accurate to one place because it only has one division on it. It only has one marking on it. So and we'll talk. I'll remind you about the rules for counting sig figs, but for this, we would write 20 or 30 without a decimal point. And then what that means is you used a measuring device that was only accurate to one place. So instead of saying 20, Instead of giving your number and then writing out or typing out, like I used a meter stick that was only accurate to one place. Like that's a mouthful, and you don't want to do that every single time you write a number. It's just not realistic. So we made up some rules to for sig figs. So right, I didn't know. All I know is it's 20 or 30. So then I take my meter stick and I divide it into tens, and then that's the whole niceness about the metric system. They divided everything by tens. Now I know it's between 20 and 30. So now I can say 21, 22, 23, maybe 24. I doubt anybody's saying 25 because that's obviously in the middle between them. But you can, I picked 22 and 23. Now it's accurate to two places because your meter stick now has two divisions on it. But again, that two and that three are estimates. That's what I'm saying. You're guessing. I don't know if it's 22 or 23. It's just, you might say 22, I might say 23. We're both right because there's no markings. So we can't argue over that. Could be 22, could be 23. Now I take those 10 markings and I divide them into 10. I get millimeters. Now I can see that here's 20, 21, 22. It's between 22 and 23. If you thought it was exactly on the 22 line, then you would say 22.0. Maybe you thought it was a little past, so you might say 22.1, 22.2, 22.3. You get the idea. At this point, those are so small that it, that last digit, that third, because we have three divisions, now we have three digits. But as you get more divisions, you get more accuracy. And that's the whole idea with sig figs. That's why we have sig figs. It's just a shorthand way of saying how accurate your measurement was without actually writing out. I used a meter stick with three divisions. All right, so a little Edpuzzle, a little bit about Edpuzzle. This one is on significant figures. This is another assignment. So finish this assignment, and then you'll see another Edpuzzle for this. But just want to talk about Edpuzzles real quick. They are meant to kind of highlight key concepts that we would normally discuss. So for this one, it's gonna review and highlight things on significant figures. You have two chances. Sorry, you're not in class, so time is not a limit for you. But you have two chances. The first chance, I would just go through it, see what you get. You get 100, you're good to go. Don't worry about it. You get an 80, 90. That is up to you. Like I'm gonna keep that, or I'm gonna be like, oh, I got a second chance. I know what I missed. I'm gonna try again and get that 100. That is what the second chance is for. But take your time with the second chance. If on the first chance you don't know why you missed the question, like you should message me. Like if you come across the question, you're like, I'm guessing on this one. You might want to make a little pulling up an email and just put it in there just in case. Um, and then for third chances, it let's just say after the second chance you're still sitting at a 90. You shouldn't email me to get a third chance. What I'm saying is if it's below a C or even a C, I know some of you get upset with C's, but then ask for a third chance. But I don't. It's not meant as like, oh, you missed one or two questions. It's more meant like I bombed it twice. I need another chance and I will go slower this time. I'm gonna ask you questions, blah blah blah. You get the idea. All right. Significant digits. So I'm gonna review them here, and then you're gonna review them in the video here. But how I remember them, and again, we're just worried about sig figs on labs. We'll practice them otherwise, but you're never gonna lose points because you mess up a sig fig. Like I want you to know physics. I don't want you to be. I'm not gonna be. I'm already picky about the physics, so I try to give you some leeway some places. But just a reminder, or if you've never seen this. So some of you have seen this before, some of you haven't seen this before. But 1 through 9, all those digits are significant. They are accurate, right? They count as accuracy. So we call those significant. So 1 through 9. The zeros. Anytime you see a zero, then you got to stop and think for a second. Does the zero count or does the zero not count? So it's straightforward. Leading zeros never ever count. Leading zeros never count. Trailing zeros only count if there's a decimal. So trailing zeros only count if there's a decimal. So there's really two thoughts in your head. Leading zeros never count. Trailing zeros, is there a decimal? Then it counts. So I'm going to do some examples here. 2.00123 doesn't end in zeros. Sorry, doesn't begin in zeros, doesn't end in zeros. I could have said that either way. So those zeros count. So that has six significant digits. 0.001230, that second one, those leading zeros don't count. You still need them for the number. That's a really small number. But they're not part of they're not telling you how accurate the measuring device was. So this one, the one's good, the two's good, the three's good. That zero's good because it's a trailing zero and there's a decimal point, right? There's a decimal point back there, so that zero counts. So that has four significant digits. Um, so it's telling you, right, that it used a device that had four divisions on it. Well, too fast. 1200, you saw the answer. 1200, there are trailing zeros, no decimal. They don't count. So you still need those zeros to tell someone that, hey, that's 1200. But they are not part of the accuracy. That measuring device only had two divisions on it. And then 1.00 times 10 to the sixth. The 10 to the sixth sometimes throws people off. That's just a million. You're just taking 1.00 and multiplying it by a million. How accurate is it is just that 1.00. Those are trailing zeros, but there's a decimal. Those count. So that has three. And then the question on there, which number was measured with the least accurate measuring device? Well, we can easily tell that it was the 1200. Even though that's the second biggest number on there, it was only measured with a device that had two divisions. Labs, this doesn't pertain to us. Sorry, you guys are doing, sorry, I'm skipping over some stuff. Lab data analysis. Okay. Uh, when we're doing labs, we want our data to be precise. So this comic here, the pitcher asks, "How was that one?" Catcher says, "You're still a tad high, but you've got a real nice pattern." When you're taking data, in that data table, you should see a pattern. Like typically, if this is increasing, or this is increasing, this side's decreasing. Like there should be some kind of noticeable pattern. That's an indicator that you're probably on the right track. If it's all over the place, like this increased, this decreased, and then the next time this increased, this also increased, like that's a sign for concern. Um, so yeah, you're looking for patterns, precision, that kind of thing. So the more the chances are, if you have a decent pattern, you're gonna have a decent lab score. And then if we need to, like you guys have 2 weeks, right? I'll catch it and then we can fix it. Uh, oh, accuracy. Sorry, what is accuracy? Define precision versus accuracy. Okay, that's nice. I was like, somewhere is accuracy. Um, Accuracy would be if all those pitches were caught by the catcher, or at least most of them, right? The majority of them. That would be accuracy. That's where percent error and percent difference come in. We'll see how close we are. We're trying to be under. I'm good with 20. Under 20, I'm good. So the difference between percent error and percent difference. Typically, I'll usually put it on the lab just to save you time because I need you to show work. So what you can do on the labs is click the equation and put your numbers in. You can retype it off to the side if you want to. I just need to know what's the experimental, what's the theoretical, what's measurement one, what's measurement two. I'm going to talk about that all right now, but uh, and the difference between the two. Why do we have two ways of analyzing data? And there's more ways than this, but the percent error. When you do percent error, it's because you're comparing your experimental, which is your measured value. That's what you get from the lab. You're comparing it to an accepted or a value that we know as fact. Right? We know it's this number or around this number for that matter. So in that case, that's when percent error is. And then you got the absolute value signs on the outside, so it's always going to come out positive. So you take experimental minus theoretical divided by theoretical, multiply by 100, you're going to get a percentage. And ideally, it's under 20%. If it's over 20%, then we need to fix it. Percent difference. This is when you have two two experimental values. We don't have a theoretical value. We have another measurement. So, and it doesn't matter which one's measurement one, which one's measurement two. It doesn't matter at all. You're going to take the difference again if it's absolute value signs, so it's going to come out positive, and then you divide by the average. That's what's on the bottom there. Multiply by 100, it's going to give you a percent difference, and then we'll do that for each lab, most likely, just to see how well your data is good, how well you did. Conversions we are going to talk about on the problems. I'm going to give you just why we use them real quick. We just we need things in the same units, and sometimes when you come across problems, they are not in the same units. Sometimes because it's a science, we're using the metric system. That is not we are not familiar with that system. Most of us, right? I tell you, I drive 70 kilometers per hour. You're like that. that sounds reasonable, 70 kilometers per hour. Uh, or in this case, would you rather drive 70 kilometers per hour or 40 miles per hour? Right? They're two different units, and I can't picture 70 kilometers per hour. So quick story here, my quick driving story. I am notoriously slow. Younger days, I got some tickets. Older days, I'll drive behind a bus for 20 miles and not realize I can pass them. I don't know what's wrong with me. So I'm driving down 64 for whatever reason. Nice day. Nobody's on the road. Like it's just us. Family's in the car. Um, I'm going. The speedometer says 70. And I'm looking around. I'm like, I am flying. Like nobody's catching me. I'm just going. I'm like, man, I am actually going the speed limit. Like I'm good to go. And then so we do this for like 20 miles. And my wife finally looks over and she's like looking around. She's like, there's no way you're going 70 miles an hour. Like there's something wrong with the speedometer. And I'm looking at it and I'm like, it says 70. So that was the digital, right? Beside it, we have an analog one with the dial. It was at 40. And I was like, what the heck? Then I finally looked. Uh, we had stopped at a little place to eat, and my 2-year-old, I had him up in the front seat. We weren't driving. He was just playing in the front seat with me. Uh, hell, you know how you can hold the button down and you can change it from miles per hour to kilometers per hour? He had changed it. Um, anyway, it changed. So what I thought was 70 miles per hour was 70 kilometers per hour, which when you convert that to miles per hour is 40. So that sorry, random side story, but that is why we're converting stuff because we are not familiar with kilometers per hour. You don't have to memorize conversions. You're going to use the ones on my equation sheet, and then once we get through this unit, once you show me you know how to do conversions, then you can just look them up. You can look them up any way you want. You can have Google convert it for you. Like it's all good. Classic is where we're going to do problems. We'll talk about that with problems. There's a lab on there. There's some activities. Translating graphs. So do you need this one right now? Yes. We are going to do. Sorry, guys. I'm thinking while I'm doing this with you. So translating graphs real quick. This will come up this week or it'll come up next week. But so this is a position time graph. And so we can tell from it is that we can look at the slope. And the slope of the line, how steep it is going to give us information about how fast it's going. So this first line, right, is constant because it's a nice steady line. So that's constant. Slope is constant. And then it's negative, right? It's going down. That's the first line. So how we would draw that as a velocity, this is called translating graphs. So you can convert a motion graph into a velocity time graph or a speed time graph. This is coming down the road. So right now I'm just kind of we're talk. This is kind of an intro to it, but we'll do more with it. So that second line. Oh, so sorry. So we know it's constant. So if my speed's constant, right, that line is steady. So if my position is constantly changing steadily, then I know I'm going at a constant speed. So when I draw that on a speed graph, I'm going to draw a horizontal line because I'm going steady, right? I'm never changing my speed. And then since it's negative, it's below the zero. It's below the zero line. And then negative signs, all that stuff we're going to talk about. Second line is also constant, but it's not, right? It's not increasing, it's not decreasing. So the slope is zero. It doesn't have a slope. And then how we draw that, which means you're not, right? You're not speeding at all. So there you have zero speed. You don't have any speed, right? The dotted lines, real quick, you can't actually go from, just gonna make up numbers. You can't actually go from 60 miles an hour to 0 miles per hour like that. You know what I mean? You have to slow down from 60 to zero. So on these graphs, sometimes what we'll do is dotted lines. Those lines, these two velocity lines are actually connected, but it's just it happens so fast that it can't fit on the graph, so we just do dotted lines. Kind of a little cheap. All right, that third line is right? Still steady, so that the slope is constant. Now it's not zero anymore, right? It's increasing this way at a steady speed because it's a nice straight line. So we get slope is constant. and the slope is positive. So how we draw that on this graph is the same way we drew it for the negative. It's if my speed is not changing, then I would draw it as a horizontal line. And again, the dotted lines are showing that I went from 0 to some speed. It's just I did it so quickly that it doesn't fit on the graph. And then that fourth. Oh, I didn't write it out. The fourth line, I drew it, but I didn't write it out. The fourth line, see how it has a curve to it? Right? That's a changing speed. The only way you can get a curve is if you change speed. So you're hitting the gas and you're going faster, 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 faster. So your speed is changing. So how you show that on this velocity time graph would be with a linear line. So this curved line over here on the position graph, right? As you go faster, 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 you cover more ground. So that's why the line's curving. Um, and then what we're saying is it's a constant acceleration. And then this is stuff we're going to cover in more detail in later chapters. But this is, uh, it goes along with graphs. So I kind of do a little intro here. And then Desmos, we will talk about later, guys. All right. That is the end of the intro.